You can start recording, Fred.
Okay, recording.
Hello, my name is Tim Weaver, and I am the president of HAL5, which is an acronym for the Huntsville, Alabama L5 Society. HAL5 is a chapter of the National Space Society and was founded in 1983 as a chapter of the former L5 Society. The L5 Society was founded in 1975 by Carol Monell and Keith Henson to promote the concepts of humanity living completely off-world in large rotating habitats as envisioned by the late physicist Gerald K. O'Neill. The HAL5 guest speaker for this month is Christopher Galea, research scientist at Princeton Satellite Systems. The subject of tonight's webinar is fusion propulsion, and the title is Direct Fusion Drive for Space Power and Propulsion. All right. Okay, you can take over from here.
Great. Thank you, Tim. All right. Let me make sure that everyone can see my screen again. All right. Does everyone see this? Oh.
Yes, looks good.
Great. Okay. Great. So I'll begin then. So hello, everyone. Nice to meet you all over Zoom. My name, as Tim introduced me, is I'm Christopher Galea, and I'll be presenting to you on the direct fusion drive for space power and propulsion. So a brief outline of the talk. We'll be going over what is fusion in the first place, direct fusion drive, and I like to just give a nice little introduction to that, so that will be brief. Then we'll go over the basic motivation and problem, why we're considering such a direct fusion drive for space power and propulsion. The solution, of course, will turn into the direct fusion drive. And this is a microfusion reactor for space, which is based on the Princeton Field-Reversed Configuration, the PFRC. I'll be explaining these two terms in more detail, the PFRC and DFD, in the coming slides. Although in the meantime, what you can see is the PFRC2 experiment at the Princeton Positive Physics Laboratory. So this is where our current experiment is, and it's in its second stage. And that's a beautiful glowing plasma that's in the center of there that has this nice purple pink color. And lastly, I'll conclude with some current progress and the path forward toward a fusion reactor in space. So let's begin with asking, what is fusion? Now, you may all come from different backgrounds of how much fusion you know or not, but I'll just go over some key points that I think are important to communicate. So as an introduction to thermonuclear fusion, fusion is the process of combining small atomic nuclei, for instance, hydrogen, into larger atomic nuclei. As an example would be helium. This releases energy. This is the opposite of fission, which is used in a lot of reactors today, nuclear fission. That's usually the nuclear power that we are familiar with. In this case, it's a large atomic nuclei, for instance, uranium, splits into smaller atomic nuclei and releases energy in that way. So if you want to go on the large end of atomic spectrum, you use a fission process and it splits and it gives energy. While if you're on the lower side, you would use fusion, you smash things together. So here's a little picture or a little image of a fusion process. So we have deuterium and tritium, which are two isotopes of hydrogen, the first element in the periodic table. And at high enough energy and velocity, they will stick together for just a bit and fuse, that's the word. And then that is unstable. So you'll end up with a helium-4 and a neutron. So I guess conversely, or in contrast to splitting an atom, you can say you are combining an atom. And so that energy that's released is a lot of energy. And per bit of fuel, you get, ends up being at least like orders of magnitude more than you would get from normal chemical fuel. So that's really great. Now, fusion occurs naturally in the core of stars. I have, as a little example here, our very own sun. This is credit to NASA for this nice picture. So our very own sun is powered by fusion. The sun, however, has a big advantage to anything that we would try to create on Earth. It's 250 billion atmospheres of pressure compared to, the one atmosphere we feel on Earth. We may never match this parameter in terms of Earth-made fusion. So what can we do? Well, in order to achieve thermonuclear fusion with enough energy gain, our advantages that we have are either to make a material hotter than the sun. So instead of 10 million Kelvin, make it 200 million Kelvin. And we can also use more reactive fuels. This is the heavy hydrogen isotopes. The sun actually uses just normal protons, which are just single hydrogen. So it ends up, it's because of the sun's great mass and pressure that it makes it work, but there are actually more efficient fuels you can use outside of the sun. So why does fusion require plasma? Because that's going to be a big part of this talk, and a lot of the fusion concepts we think about, we're trying to control and contain this substance called plasma. So at fusion temperatures, let's say around 100 million degrees, no matter exists in the solid, liquid, or gas phases. All matter exists as plasma, which is like an electrically conductive gas. I have here a nice little states of matter, and you would remember the usual states of solid, and then you heat it up enough and it becomes a liquid, let's say ice to water. You heat that up enough and it becomes a gas, like vapor. But if you heat that up enough, the electrons get ripped off and you have this electrically conducting gas fluid called a plasma. So this is good for us because plasma can be confined with large magnets to keep the heat from leaking out and cooling the plasma. These are called magnetic confinement types of systems. The trick of artificial fusion, the fusion we're trying to create on Earth, what's made it so elusive is keeping the plasma hot. The heat leaks out, or the heat that leaks out must be replaced via heating systems. So we have to continue to heat the plasma, and it continues to give off heat as well. This has driven reactor designs toward larger structures, stronger magnets, and higher heating power. And the PFRC is one example of a fusion reactor concept that we're trying to achieve net energy in, and ultimately power reactors and go to space. So the promise of fusion is that it's power that's abundant. One, basically the fuels are made from abundant elements, let's say hydrogen or low atomic numbers, and only small quantities are needed. For instance, 100 pounds of fuel could power New York for a year. You contrast that with like normal chemical fuels or oil, and you need a lot more in order to power New York. So the required resource extraction is minimal. It's safe, so fusion reactors cannot melt down, at least in the typical way that we understand, I guess, the negative cases of nuclear reactors to melt down. So when you think of Fukushima or Chernobyl or 3 Mile Island, the fusion reactors, because fusion is very hard to start and easy to stop, you don't have to deal with these same concerns as in the other case of a fission reactor, where it's very easy to start, but it's harder to stop. So some fusion reactor designs produce some radioactive waste, but in small amounts and short-lived. Lastly, this power is clean overall. Fusion reactors do not release carbon dioxide or any other pollutant, so not contributing to climate change or to ecological contamination. So last thing that I want to introduce here before we go into the meat of the talk is, what is a field-reversed configuration? And also, let me just see if there are any questions so far. Has a practical form of fusion energy been achieved at the present time? So there are many companies working toward making a practical form of fusion energy, but no fusion concept has yet achieved net energy gain to produce more energy out than it takes in. So hope that answers your question, and let me know if you have follow-ups on that. So what is a field reverse configuration? So this is the main configuration we'll be considering in this talk. It's FRC for short. And it's one of many, that is, more than 10, 20, 30, depends on how many you want to count, design approaches to contain hot plasma with magnetic fields. This one was actually discovered by accident in the 1960s plasma experiments. They were called theta pinches. And essentially, you would, if you see these coils here that are in blue, you would send a current going in one direction, let's say counterclockwise, and then you would very quickly reverse the current to go clockwise, and it would compress magnetic fields and make this nice closed configuration. And scientists noted this, and they're like, oh, that's very curious. And then we found out that it was a pretty neat configuration with a lot of pros to it. So that's kind of what has led us to considering it today, for instance. There's been a good amount of research, obviously, since the 1960s on it. It's a linear array of magnets, which is really great. And we'll compare that to a few other designs later where you have magnets that go wrap around a torus or a donut and are very bulky. So having just an array that goes linearly is very space efficient. There's a strong azimuthal plasma current, where azimuthal is essentially this red arrow direction. It's, if you want to think of it as counterclockwise. And most of modern day work is investigating the stability of these configurations. I'll point out for later, for future reference, that these over here, these lines that kind of wrap around the plasma are the magnetic field lines. And so there are some that begin outside and end outside of this plasma. But then we also see, if we look near this, in this green region, that there are lines that completely close on themselves. They basically start here and end here. And that's really great for confining plasma particles. The plasma will want to stay in those, along those lines. I guess no pun intended, but it would stay along those lines, and you would be able to keep the plasma in the reactor for longer. Okay, and just to finish up this section of the talk, the advantages of FRCs to the more mainline fusion reactors, such as the tokamak or the stellarator. And you can see them here. This is the FRC that I showed earlier. And then a tokamak, which there's a very famous one that's in France being built. And also, if you've heard a lot of the news from the MIT spin out Commonwealth Fusion Systems, they're working on a tokamak. And same as with a stellarator. So tokamaks and stellarators are both donut shaped. They look like a donut. And so you have to deal with a lot more shielding and size of magnets, and ends up being much more complicated. So in short, the FRC is compact. It doesn't need any central magnets. It's nice and cylindrical, so easy to construct and maintain and simple to build. And then it has a high beta. Beta in plasma physics jargon is basically the ratio of the pressure of the plasma, which is like how dense and much and hot is the plasma, to the magnetic pressure, how strong are the magnets carrying it. So for the same magnetic field, you can now handle a much hotter temperature plasma or a much denser plasma. That's great to achieve higher temperatures so that we can use as reactions that are cleaner but require higher temperatures. And I'll go over that in a subsequent slide. Great. So since we finished this section, let me just quickly look at the Q&A and see if there's any other questions. Is cooling required? So there is, I have to think about, yes, so there is cooling required. It's primarily for the magnets. A lot of times we want to try to use superconducting magnets, and superconductors work at low temperatures, let's say less than, I don't know, 200 degrees below zero or something. And so in order to keep those magnets cooled, you need to cool them with some kind of cooling fluid. What is a present ratio of energy in comparison to energy out being achieved? So it depends on which reactor you consider. One of the closest ones would be JET, which is the one in the UK. They got, if I recall, up to around, I think it was around 50% or a little less. Although that might have not been including some other energy sources, but it is a pretty promising next step for the tokamak, for instance. And then I think Mike is asking about the FRC. So the FRC, very quickly, is a field-reversed configuration. So just remember this nice compact configuration of a plasma. Yeah, great. So let's go over the motivation and the problem that we want to address. So the problem, and now bringing this to space, and probably what you're all here and interested to learn more about, a key problem is slow and expensive deep space missions. So today's deep space missions are too slow and expensive to enable the kind of interplanetary travel imagined by science fiction and aspirational NASA roadmaps. If we look at an example of New Horizons, right, which flew by Pluto in 2015, that took 10 years to arrive to Pluto. So, if we're thinking about missions, these are like decent chunks of people's scientific careers. All of you were 10 years younger when it launched before it landed, right? There's also compromises in cargo mass, that's payload, what you can hold on your spacecraft, and power, right? And so these compromises limit the capability and also the data return of these different missions. So long trip times also imply that some deleterious consequences, some dangerous ones, you could say. So for instance, there are large radiation doses that one would have to deal with over a long trip. So that's dangerous for humans, of course, but it's also damaging to spacecraft components. Also, the increased expenses for staff on mission is also a result of long trip times. And scientists might even retire before the instruments reach their intended orbit. So wanting to lower trip times is really important for deep space exploration. Let's see. One question. Yes, if I will be able to provide a link to your PowerPoint presentation, I will figure that out with my boss and the committee after this talk. But thank you. Yes. So what are our propulsion options? What can we do? So we have a few options to consider. I have a little outline here in this nicely produced graphic by it's called Space Ventures. They're helping us out with a few things. First example would be chemical propulsion. So you're all pretty familiar with this one. If you see any rocket that gets into space, you see a lot of fire coming out of it. That's chemical propulsion. This is thrust via reacting fuel mixtures. So chemical propulsion has a high thrust. Of course, you need high thrust in order to even get out of Earth's atmosphere, but low exhaust velocities. They're closer to, let's say, 3 kilometers per second. Electric propulsion, on the other hand, where you now energize heavy ions and you shoot those plasma particles out, that has high exhaust velocity. So we're getting to 45 kilometers per second, but it's generally low thrust, less oomph, I guess you could say, to your spacecraft. And in fact, we cannot use electric propulsion to get from ground to space. And it's limited by power as well. Nuclear thermal propulsion, which is a little bit more novel, it uses fission, not fusion. It thrusts basically via fusion heated propellant. It has modest improvements, but it's still pretty early stage. And then if we consider some mainline fusion reactors, they're too large. So the tokamak or the stellarator that I showed before, and they also don't have a direct thrust mechanism. It would be like the nuclear thermal propulsion, where you would heat up some kind of fluid and you would send it out, propellant, right? And so you can see some estimated trip times of 18 months or more, 9 months, 5 months, and fusion would be the most promising, going down to 2 months to Mars. So that's a little comparison there. So a direct fusion drive, where fusion energy is emphasis on directly, converted to rocket thrust, could reduce total mass per unit power by a factor of 10 or more, and hence enabling rapid trip times while greatly reducing fuel requirements. So that will be the focus of our talk, is this potential solution of the direct fusion drive. So before I get on to the next section, what are the different forms of plasma / fusion propulsion? So there are not too many fusion propulsion forms. I mean, a lot of them, like I said, require just whatever fusion reactor you're using to heat up the propellant and shoot it out, or to produce electricity and hence drive like an ion drive. But in terms of direct thrust, we are one of the ones discussing that in particular. So that's a really nice innovation of the PFRC. So another problem with long trip time for your list: time value of money for the flight assets before they can produce results, or revenue for a commercial mission, making investment difficult. That's correct. Yes, I did not get to go into all the implications, but David has a good point that there's a lot of implications on having long trip times for missions. And then, can the plasma already in space be somehow incorporated into a propulsion system? Carl, you might want to follow up on this with another question, because I'm not sure what you quite mean by this one. But just to answer your earlier question again, that different forms of plasma propulsion, there are some that don't require fusion that are the electric propulsion types, where you shoot out a plasma, but it's very low power. Okay, so let's go now deeper into the solution of the PFRC/DFD for power and propulsion. Here's a nice little image of the basic system, and we'll go over it in the next few slides. So it's basically a dual-use technology, and that's why I've been describing the PFRC/DFD. And so we can divide it by this left-hand side and right-hand side. So the PFRC is the Princeton Field-Reversed Configuration. It's essentially an FRC, the Field-Reversed Configuration, in a mirror. A mirror is basically where you have two really tight magnets at the ends and distributed magnets in the center, so that the plasma bounces back and forth. It's like a magnetic bottle. It basically, plasma likes to go to one end, and then it bounces back to the other, more or less. RF heating is used, so it's radio frequency heating to heat the plasma. And then just to go into a little bit more detail, there's an external cool plasma flow, which removes the fusion exhaust. So the basic principle here that's going on is that by passing this cool plasma along the fusion heated plasma, so right here is where the fusion is happening in this orange section, while this cool plasma, which is, I guess, green-blue, aquamarine, is being sent around it in what's called the scrape-off layer, or the gap. And as it's sent around it, these hot particles that sometimes leave the plasma heat up the cool gas and the cool plasma. As it heats up, it then gets sent through another mirror coil and gets sent out through an exhaust. So this energy can be collected, and now you have something that can spin a turbine, or create energy, right? That there is cool and this is hot, essentially. So now let's see how we can transfer that to the direct fusion drive. So the direct fusion drive is very similar, except as we see, there's not an exhaust box. Rather, we open that end, we crack it open, you could say, and we let that exhaust plume go out. And as you can imagine, that's thrust, that's an exhaust. We can propel a spacecraft with that. So now it's a really neat concept because we're taking this cool plasma flow, we're heating it directly with the fusion products, and we're just sending it out directly, out into space. We can also adjust external flow rate in order to produce a desired thrust and exhaust velocity or specific impulse. This is what we call thrust augmentation. So we see that we can actually achieve power and propulsion in one device. This can still achieve power because there's some heat transfer that happens on the edges of the plasma. And so we can use that for energy generation at the same time. So let me see before I go further if there's any other questions. Yeah, if your fusion reaction is producing a lot of high energy neutrons, is that a problem for your spacecraft, especially a crewed spacecraft? Very good question, Daniel, because that is going to go into the next section of my talk. In short, I'll say that this is this type of fusion configuration, and in fact, why we use this D-helium-3, which I'll talk about soon, is in order to minimize the neutron load. So we'll talk about that very soon. So how does it work? Let's just go a little bit more into detail with some nice graphics here. So we want to use the PFRC, the Princeton Field-Reversed Configuration concept, to create a direct fusion drive, DFD. The PFRC is a fusion reactor concept which is small and light enough to fit on today's launch vehicles, which makes it stand out. So the DFD will allow deep space missions to fly directly to the destination rather than having to use complex gravity assists from other planets. So that's another neat point about the DFD. So, so getting into how it works. So we start with a linear arrangement of magnetic coils, which confines the plasma. So these magnetic coils basically shown here. And so, and then this plasma is the glowing pink region, you could say. Then we have these radio frequency antennas shown as these rectangles spaced out. And these radio frequency antennas are used to spin the plasma and heat it up to heat it to fusion conditions. Then we enter in, or we send in a cool propellant, this blue propellant from the left, and it gets sent around the hot pink plasma and heats up. And so it extracts energy from the fusing plasma. A strong magnet at the end shoots out the energized propellant out the opening in order to generate thrust. And then the flow rate of the propellant, as I mentioned before, can be adjusted to produce a range of thrusts and exhaust velocities. Okay. So it seems like there are a few questions coming up, so let me just make sure those are addressed. Since most of the visible matter in the universe is made of plasma, I wonder if this natural resource could be utilized in any plasma propulsion system. That's a really neat point. So in some ways, yes, I think a very detailed answer to this would be difficult. The tricky thing is that we want to make sure that the plasma we're working with is very high density and very hot. And so a lot of the plasma in the universe, unless you're in a star or something, a lot of it is cooler or very low density. So that's the tricky thing of utilizing it directly. But we have talked about utilizing abundantly appearing fuels that come in space. And so that's connected to some of the plasma physics as well. Let's see. Anything else? Yes, the field coils require active cooling. Do you see a direct fusion drive as an in-space only propulsion, or is there a version to also allow launch from the surface of the Earth? So for now, basically it would have to be in space only. Essentially, up to this point, the only thing I can really do off the Earth propulsion is chemical. It's a mix of the thrust, but also you're working with kind of low pressure conditions for a fusion reactor, right? You're not putting it in the atmosphere. So let's see, any other questions? What amount of funding would be required to demonstrate the DFD in space? That's a good question. I think it ends up coming out to, I think that's like $40 million or something. Now, and that sounds, or no, maybe it might get up to 100 million. I can check with my boss on that one. But the key thing there is that when you compare to a lot of the big reactors, and we'll compare that later, like the tokamak or the ITER in France, that's one of the tokamaks. There's already been $25 billion worth of funding into that. So it does go to show a sense of scale that asking for even tens or hundreds of millions of dollars is actually not that bad in comparison. How does RF work to get energy? I'll explain that in a future slide. What temperature are the cool and hot plasmas? So hot plasma, I guess I would normally work in EV, but yeah, in Kelvin, you could say hot plasma would be like 300 million Kelvin, while cool plasma is maybe like 1 million or less. It's a bit of a misnomer because you think, oh, that sounds so hot, but electrons get hot really quickly. And so for like 1 voltage of energy, they have like 1,000 or 10,000 Kelvin to them. So that's one thing to say. What provides energy to the magnets while the spacecraft is in space? So that would be using some of the energy from the output of the fusion drive, or the energy production aspect. What propellants can be used? So we would be using deuterium and helium-3, which I'll go over very soon. And let's see. Are there any plans to utilize the helium-3 when we begin colonizing the moon? So yes, that is something that we have discussed about different types of helium-3 for our spacecraft. That's right. Moon mining, there's like gas giants mining, etc. Yeah, also, Tim, I think I answered the first 2 questions, and then let's see. Yeah, I answered these 3. So, yeah.
Wait, hold on. I don't know if did you answer the one from David?
Yes, I was saying, I was agreeing that that's an issue.
Okay. So also, so you done with all the questions?
Yes, that's right.
Okay. I do have one other question.
Yes.
Yeah, you mentioned that this was that the flow of the current would reverse in the coils. Would this make the field reverse configuration a pulse system?
Okay, so I should have been, I didn't clarify that. So that's how the first field reverse configuration was created. So that was way back in the 1960s. Our system, although it is pulsed right now, because we're working on stability research and other things, it's meant to be continuous. So that is, so basically the antennas would go continuously and just spin around like oscillating. So the alternating current, not physically spinning. Yes. So does it answer your question, Tim?
It does.
Yep. Great. Okay, great. Thanks for your questions, everyone. Really neat questions here. Okay, so let's get to the last few parts of describing the PFRC and DFD. So it's propulsion and power generation in one device, as I mentioned before. Now, a key thing about power and why we're interested in that for space is that having large quantities of power upon arrival at a deep space destination is critical for collecting and transferring data and also supporting people. For instance, let's say a lunar base or a Mars base, right? So we do need a good amount of power to be used even when in space or on a planet, for instance. So conventional generators output hundreds of watts. That's pretty conventional. A PFRC engine, if it's in propulsive mode where it's sending primarily thrust out, it could still produce like tens to hundreds of kilowatts. So that's 10,000 to 100,000 watts. While in the reactor mode, it can generate up to megawatts. So that's thousands of kilowatts or 1,000,000 watts. So this is a pretty big deal for energy in space. And so just going over the last two parts of this little nice diagram, we see that extra heat from the fusion reaction is collected and converted into electricity in order to power the spacecraft instruments. We can basically use the heat that's coming off of the plasma over here, while we also do thrust. And by enclosing the plume, by making a gas box, as we mentioned before, the engine switches to maximum power generation. So just to conclude this section, I'll show a nice these nice CAD models made by an intern of ours, actually. She did a really great job. Her name is Zoe. And it shows a human for scale. So, right, it's basically around 2 meters tall. And it's like around 5 meters or more in length. And we see the difference between the direct fusion drive of a thruster and the PFRC as an energy reactor, which has a closed part of the system. All right, so before I move on, looks like I have one other question. How does the plasma temperature of the Princeton plasma device compare to the Vasimir drive, which is currently in experimental phase? So yes, I need to remember their temperatures, but we are a lot hotter. Vasimir is not trying to do fusion, so they don't need to get to the hundreds of millions of Kelvin. They're something that's much, I would probably say like a few orders of magnitude lower. But I should double check the exact number, and you can find it online, but yeah. Okay, so PFRC DFD innovations and unique features. Let's just go into a little more detail about what makes it unique, and this will also answer some of the questions that people had before as well. So let's introduce it with asking fusion. Why is it always 30 years away, right? I don't know if some of you grew up, and this would be before my time, in the 60s or 70s or 80s, and there is a lot of talk of, okay, we're going to achieve fusion, sometime soon, or sometime in the next 20 years or 30 years. There's a lot of reasons why it has been 30 years away, and people are a little too optimistic about the engineering challenges and other aspects of these reactors, and even the physics for that matter. But I digress. Some things in short about why even the current reactors are still 30 years away can be shown with a really great example, in the sense of it's a great project that people have been working on, a beautiful plasma experiment, but is going to take time. And that's the ITER research reactor. ITER is like the International Thermonuclear Energy Reactor for short. I think they might have changed it at some point. And you can see this person for scale. So here's a little person. And if you remembered our reactor before, the person was like around the size or height of the reactor. In this case, the reactor is so huge, right? So ITER is going to take a good amount of time longer, right? It took like tens of years in bureaucracy, tens of years of design. It's been taking, I guess they started design more than 10 years ago, or building more than 10 years ago. And they're going to hopefully finish up in 2025. And then they're not going to actually test the real fuels that they want to test until 2035. So you see that there's like this kind of, and then even after all of that, this is actually a plasma experiment. We are waiting for a next design phase for something called GAMOW, which would happen in like 2050 or 2060. So fusion's a long time away in some sense, right? So yeah, the reasons for this are that it's really big. We're talking like 1 to 4 gigawatts. That's billions of watts. And this is like 60 meters tall, really tall. The problems are too hard, you could say, in the sense that tritium, which is one of the fuels that needs to be resupplied and is pretty, has some scarcity on Earth, it has to be bred. I guess people would debate about the term scarcity, but it's not abundant, let's just say. And so you need to breed tritium, which is a very complicated process. And you also have to deal with these high energy neutrons, as someone asked before. These high energy neutrons destroy the walls, they activate the material. It can be an engineering nightmare. And lastly, it's so expensive, right? ITER will cost in total $65 billion. That's a lot of money, right? And this is an experiment. Once again, I do think it's very beneficial that we are putting money and time into this effort, but it's showing that these are the reasons why fusion is such a while away, and why it's important to look at alternative configurations or alternative approaches that could be faster. And yeah, other similar machines will cost about the same when we add it all up. So let's actually, I guess right before I go into that, let's see what this one question is. Would a microgravity condition on the ISS, for instance, be more conducive to experimenting with the fusion process? Yes, to some degree, yes. Basically, you have to deal less with pumping down your plasmas and your gases. And then also like there might be a few other things. Gravity, you don't really have to worry about too much in the first place. So yes and no, there would be some benefits to it. But I would say it wouldn't really move fusion along too much, aside from there might be some interesting experiments one can do at the very least. Let's see. Okay, so then let's introduce now the Princeton FRC, the PFRC that we've talked about. And as a recap, Field-Reversed Configuration is the FRC. It's simple, small, and clean, right? So we had these kind of in contrast to the big, hard, and expensive, if you want to almost a point-by-point comparison, simple, small, and clean. So what does that involve? So simple in part because it has a linear form. If we see tokamaks, for instance, we have to deal with this whole center magnet stuff going on. And hence you need a really high magnetic field here that goes in order to make just a normal magnetic field in the center, or I guess in the center of this part. And you need a lot more just magnet cooling systems, weight, it all adds up basically. It's also, we have a single RF heating system. So this is the RF heating antenna here. It would technically be distributed along the machine, but it's nice and simple and straightforward in terms of the type of the engineering. And we are conducting research and investigation on this type of heating mechanism, essentially as we speak. And then lastly, we have a natural jet. So we have this natural jet that goes right into space, which is really great. It's small, it's 1 to 2 meters in diameter. That's pretty great. And we're looking at the 1 to 10 megawatt scale. So that's about 1 million watts instead of 1 billion watts. And you can actually do a lot with that as well. Let's see. And lastly, it's clean. So this is starting to address what someone asked before about neutron load. So instead of using deuterium tritium, where D is for deuterium and T is for tritium, those are 2 hydrogen isotopes. Rather, we're using deuterium helium-3. So a hydrogen isotope with a helium isotope. And the neat thing about this, which I'll go into another slide, is that it's very low neutron output. And in fact, it produces more protons, which you can control with magnetic fields. So very low radiation, which is really great. So just to go in a bit more detail, simple is the linear array of coils. So we showed these coils cross sections here with these little X's through these blocks. The linear configuration means that the reactor could be assembled in segments and simply pulled apart as needed, right? We don't have to worry about building or putting away something like this, right? That's a really nice contrast. Next, it's small. So for contrast, if we see a person for scale, compared to 60 meters tall and development in 30 to 50 years, we're 2 meters diameter, so you can say 2 meters height, and the development is more like 5 to 10 years. So that's a very different time scale. It's also small enough to fit on a single launch vehicle. So that's really great for space, of course. And now let's go over the clean part. So I know this slide has some equations and stuff. So not to focus on that, but just to say that the main fusion reaction, which is deuterium and helium-3, and it produces the conventional helium, helium-4, and a proton, is 98% of the power. These side reactions, which are, you could say, the bad reactions, which lead to neutron output, either indirectly through the tritium or directly, are less than basically 1% of the reactor. So, or I guess less than 2% at least. So instead of having 100% or a very high percentage of your power in neutrons, and so you have to have tons of shielding, we're dealing with 1 to 2% of neutrons. So it's a much easier shielding process. And so that's to answer the question from before about shielding, that it's not as bad. And also, there's another note that the tritium itself, another way that we help minimize the neutrons is that the tritium gets cooled and exhausted before it can fuse in a lot of cases. The tritium has a very high, large gyro radius because it is, it's more massive. So it kind of goes around the field lines in a larger circle. And so it leaves the plasma a little faster. And so you can just shoot it out of the plasma and don't have to worry about it producing neutrons. All right, so actually, before I move on, since that was a good bit, let's just see. Considering all your talking points, sorry?
Oh, I was just wanting to ask you something real quick. You mentioned there was a question about producing about getting helium-3, but I couldn't help but notice that the deuterium reactions produce helium-3. So I was wondering if maybe you could get your helium-3 just by running pure deuterium through your machine before your mission, and then when you launch it, just use the helium-3 from that.
That's a really good point, and actually that is something that we talk about sometimes. It's called a DD breeder, essentially. So it's you use it's a possibility of using like a deuterium fusion reactor that would basically breed helium-3 for you, and you can save that for your mission, or maybe produce it while you're on your mission, right? If you have this extra reactor that you can fit on your spacecraft. So that's a great suggestion, Tim. And yeah, it is something that we have considered. So considering all your talking points and the relative costs involved, why aren't there several different research groups rushing to demonstrate PFRC power generation on the ground and beat the ITER and other multi-decade projects? So that's a really good question. So there are many companies that are trying to beat ITER. In fact, that's technically Commonwealth Fusion Systems slogan, right? Is that they, what's it called? Yeah, that basically they want to make a higher magnetic field version of ITER, right? So in terms of why us and not anyone else, I mean, the actual ideas and the invention of a specific type of heating mechanism that allows this to be possible, and also the patents that came around this weren't actually discovered until the 90s and early 2000s. And in fact, that was by Sam Cohen, and then my boss, Mike Paluzic, and others worked on the design of the fusion drive, basically. So a lot of that is relatively new, I guess you can say, in terms of the scale of fusion timelines, right? This is like 20 years ago or something. And aside from that, basically, we have been like steadily working on this and progressing, but there are also there are uncertainties, there are risks. I can't go into all of those in the context of this, but if you have further questions, you can email me and I can go a bit further into detail on that. So it's essentially like a high risk, high reward kind of thing. And there's only so many people and so much time, so people try different types of reactors and configurations. So that's to try to summarize some thoughts on that, but I could probably talk 30 minutes or an hour to give you a full answer. Has any consideration been given to doing fusion research with the concept of quantum mechanics processes? Yes, actually. So one example is spin polarized fusion. So if you know from quantum mechanics, electrons and atoms have something called spin, right? It's like either it's kind of like an angular momentum. It's like a spinning top, but it's not quite. That's a whole nother lecture for its own. But basically, things can be spin up or spin down. And then there's more complicated systems as well. And it's quantum in a sense that it can only be spin up or spin down. It can't be like spin sideways or something. And yeah, it turns out that there's been research, at least theoretical research done on if you made all of your spins of your, let's say, deuterium and tritium all spin up, you might actually minimize the, you might actually minimize the interactions and the fusion process of an unwanted fusion reaction, right? So if you're concerned about deuterium and tritium, you can, or like maybe deuterium even, you can make sure that they're all polarized in a certain direction and mix them together, and so they won't fuse as much. Anyway, so that's one point. So historically, not only the coolant passed out the end of a theta pinch device, but also the fuel. That's what led to the torus configuration. How has performance improved in this regard over the past 50 years? Maybe I should clarify which way you mean. So in terms of the theta pinch device, there's been improvements in terms of like an FRC, and the FRC that we're making is not like a normal theta pinch. It's basically, we're creating the FRC with radio frequency fields. And so you get right to the nice closed magnetic field topology. Now, I think you might be talking about like mirrors in general and how they are not quite closed bottles. They let a lot of stuff out. So yes, we are working on improving confinement. There's been encouraging studies and computations of getting good confinement in these reactors. But that's part of this is the research and development that that's part of my job description, right? In what ways does the Princeton Field-Reversed Configuration differ from NearStar's hypervelocity gradient field fusion concept, which also offers dual use? Yeah, so hypervelocity gradient field fusion concept, from the bit that I know about it, I actually know the CEO there. He's a nice guy. He's also named Chris, actually. So they basically compress these kind of like these, they magnetically compress these, I guess, tablets, if you want to say, and shoot them out. And it's a pulsed method, right? So that's one of the main differences, is that you're sending in things and trying to pulse them. I also don't quite know the size comparison. Stephanie Thomas, who is the vice president at Princeton Satellite Systems, knows a lot more details on that. So feel free to email us if you have questions on that. How does your concept compare with other FRC experiments such as TAE? Good question as well. So yeah, there's TAE and there's also Helion, our two other FRCs. And they're also making a lot of money too. That's kind of an interesting tidbit on that. So TAE, okay, both of them. So each FRC uses a different type of heating method. TAE is mainly using neutral beams. So to spin up the plasma, they basically just shoot in neutral particles and bombard, basically like if you're trying to spin like a tire, like a bicycle wheel, you like push it on the bottom this way, and then you push it on the top in the opposite direction. So that's what they do. They basically shoot neutral beams at the top and the bottom. And that requires a really big reactor because those beams won't mix enough or transmit enough energy if the reactor is too small. So they're constrained to big reactor. In fact, they say that the size of their reactor is like 2 school buses put back and forth. So that's big. Helion has a little bit more, I guess, private security stuff. It's kind of harder to get to some of the meat of their concept stuff. But the basic idea is that they are trying to do a merging compression. So they produce 2 FRCs. They send them down these like magnetic field tunnels, you could say, and they push them together. And that one is pulsed. So you have to deal with very high temperatures and densities in a pulse configuration, and that wears and tears on the system. So that would be like some comparisons. I have a slide at the end if you wanted to look more into that. I presume you think a PFRC type power reactor would come before a fusion rocket, or do you think the rocket might come first? That's also a good question. So I think more likely the former first, because you can test the fusion reactor on ground quicker than getting it like a whole space flight ready and test and everything. However, in part, it actually depends on funding, right? So there's different types of funding environments, right? And some of them are very big on propulsion and some of them are very big on energy. So if a funder comes along, or let's say Department of Defense or something, and it's like, hey, let's try to send something to Mars, then that would speed up our timeline for the rocket part. So yeah. Great. Let's see. Okay, so I've been hinting at this a lot, but this is one of the main, scientific breakthroughs that really allows a PFRC to do its magic, you could say. And it's unique heating. So it's an RMF not current drive is what it is in short. So RMF, I guess I should have put that on the slide. RMF stands for rotating magnetic fields, and the not is odd parity. So you can see that pretty well in this bottom figure, this right bottom figure. So essentially, these antennas are creating magnetic fields that go through the plasma. If you looked at the right-hand side of the plasma, you'll see that these black lines point up. These are the magnetic field lines that are being created by the antennas. On the other hand, you see that the magnetic field lines point down on the left-hand side. Both of these would be rotating in time, but they'll always be, I guess you could say, flipped mirrored-wise, and then always flipped up to down, I guess you could say. And so that's what odd parity is. So until Sam's paper, Sam Cohen, who's the original inventor of the PFRC, until his paper in 2000, so that was 22 years ago, basically all FRCs were with the left and right pointing in the same direction. And so that's an even parity RMF. So this odd parity is really neat because it basically allows the field lines to stay closed even to perturbations. The tricky thing with the even parity cases, and what limited them so much in temperature, is that for explanations of the physics that are maybe a little bit more over this talk, you would end up, instead of the field lines being completely closed and like a bubble of the magnetic field, there would actually be opening of the field lines and particles would escape. So you would have less confinement. And that's a big impediment to trying to heat it, trying to contain the plasma, etc. So our heating method basically flips the field direction, making all the difference in plasma confinement and heating, in short. And you can see right here, these are two antennas next to each other, where the red arrows are like the current in the antenna. And they're going opposite, so that one of them creates a magnetic field going up and the other one makes a magnetic field going down. So odd parity heating produces closed field lines that improve plasma confinement. The current is driven and it's steady state. So that's what I was saying before, that we're not a pulsed, our concept is not a pulsed concept. The antenna currents create rotating magnetic and electric fields that rotate and spin the plasma up. They drive an azimuthal current, which is spinning the plasma essentially, since current is just a movement of electrons and ions. And the ions are also pumped up in energy as they rotate. And so we have many simulations showing that we can get to these high temperature conditions with RMF. And I have some backup slides in case people were interested in that. And also there's papers if you want to read papers. This is distinct from the heating methods in tokamaks, which tokamaks use like 4 different heating methods. These two are electron cyclotron resonance heating and ion cyclotron resonance heating. So basically you try to send in waves to resonate with the movement of ions and electrons. So that requires like microwave sources and RF sources. And then there's neutral beams, like I mentioned before. And then there's also induction, where you literally just send a huge current through a plasma column or through a a current stack, and that huge change in time of the magnetic field induces an electric field that heats up the plasma. So anyway, there are many different ways of heating, and our way of heating is very unique in that sense. So why build a small, clean fusion reactor? Well, actually, I guess before we go into that, it looks like there's a few questions. So when do you expect to achieve break-even? So that depends a bit on the funding path. We have some timelines at the end. If I recall, I think it would basically be, so we're making a next reactor that would be testing the physics and getting near the break-even regime, but not quite. And so that would take a few years in order to do that. And then the reactor after that, which is the final test, is meant to achieve break-even. So I guess that would be around at least, let's say like 2028 or something. That's really off the top of my head. I have some slides later on that. Are you saying that by rotating magnetic fields, you are creating energy? That's an interesting question. So yes and no. You can argue that it's really the rotating electric fields because antennas produce magnetic and electric fields. And so it's really the electric fields that are doing the work. Because if any of you have like a beginning physics class, high school physics class, you know that magnetic field does no work, right? But electric field does. And anyway, electric fields and magnetic fields are involved. Is your group's email addresses at the end of your slides? Yes, my email address and the company's contact information and website will be at the end. And a wild thought, can a revolving magnetic field cause frame dragging, thereby influencing the dimension of time? Ooh. Well, if we're thinking about, this sounds like a special relativistic effect. So you really need to have high enough magnetic fields to deal with that kind of relativistic time change. So we're not in that regime. We do have some fast ions and stuff, but it's a little different. So, but an interesting thought. Yeah, you can maybe ask a gravitational physicist. Maybe they have some interesting thoughts on that too. Cool. So why build a small, clean fusion reactor? So the PFRC will produce 1 to 10 megawatt electric energy per minivan size reactor, in short, with almost no radiation. So this has a plethora of missions that would be enabled by this technology. We have civil missions, including distributed and remote power, emergency and mobile power, modular power plants, load following, supplement to wind and hydro and solar. So there's a lot of great civil applications. So something to note. There's also space applications, as I'll go into a little bit more in some later slides. So although I guess maybe the talk is coming to a close soon, because it's already 9, right? Tim, how much more time do I have?
Let's see. Normally I'd say about up to like about 12 more minutes, but since you're answering questions as you're going along, you can go a little bit past that.
Okay, sounds good.
Really, that 15 minutes is there for answering questions.
Oh, okay, great. So yeah, I think I'm doing that then. Great. Thanks, Tim. So yeah, for space, we have deep space missions, lunar and Mars bases, asteroid and comet mining and intervention, space power platform power, and high power Earth satellites. And lastly, for military terrestrial, we have submarines, UAVs, surface ships for deployment, remote locations and bases. So a lot of applications in short. And then I just want to, I think the last key detail or interesting mechanism is the natural thrust mechanism that I want to just talk on just a little bit more. So as I hinted at before, PIC, which is particle and cell modeling, it's a very precise thinking about the charges and how they interact type of modeling tool, shows that the fusion products will lose their energy to the shell layer electrons in just milliseconds, showing that we can get a nice efficient coupling. And sorry, we can get nice efficient coupling from the inner plasma that's really hot to the cool plasma layer that will shoot out the end. And so that's actually illustrated here by some U-edge modeling. So U-edge is like a magnetohydrodynamic code. And so it shows that the energy transfer to the ions, resulting in velocities of up to 100 kilometers per second. So that's like a specific impulse of 10,000 seconds, which is also seen in the particle and cell simulations. So basically, in short, what this figure is showing you is that as you go along the machine, so this is the first part, and this is the exhaust end on the right, these cool electrons get heated and they get sent out, get heated by the fusion reactions, and then get sent out nice and hot and produce thrust. And in fact, we would probably produce exhaust velocities on the order of 80 to 300 kilometers per second, and thrust from 5 to 100 newtons. So that's higher than electric propulsion systems, which are usually in the millinewton or tens of millinewton, although it is less than chemical. And so it's kind of a nice in between in that kind of thrust range, but has a nice efficiency to it. And so yeah, there's basically a thrust envelope at each power level where we can choose a mass flow rate and a power and get a certain thrust out for that. See a question? Can this be scaled up? So yes, in principle, yes, you would basically scale up by putting multiple fusion or direct fusion drives together in parallel, right? So as I showed in I think it was like the first slide of my talk, I had like 4 thrusters coming out. So you can scale it in that sense, yes. I'll go over this very briefly, but just to say that we have, like with the help of NASA funding and other funding, we have gone through all the subsystems that are important for a direct fusion drive, and we've sized them and made sure that they can fit into a rocket and that they have the right amount of energy going in and going out and everything. So we've done the work thinking about these things, basically, is what I want to conclude from this slide. If you have questions on this, let me know later. And this, I just want to show another great model from the intern that shows a more representative size of the DFD. If you see these a very white layer, and then in the inside, it looks very dark. The reason of that, or like this faint glow, the reason for that is basically that once your plasma gets so hot, it actually isn't glowing as much anymore. Basically, you see plasmas in a certain temperature range because it emits optical light that we can pick up by our eyes. But a plasma that's so hot will emit mainly X-rays and other things, which get absorbed by the walls, no worries. But since it's emitting those types of emission, you don't see that with your eye. So anyway, that's why I thought this is kind of a nice model for that. Would you be able to give this talk to a local AIAA group? I am canvassing for the next season's programs for the Long Island section. If so, how do we contact you? We can look into that. Greg, if you can just message me or email me, I'll have my email at the end of the talk, or contact Princeton Satellite Systems through their website. So either way, get in contact with us and we can see what we can do. This is a low label drawing, just showing all of the components that go into such a reactor. Okay, and so now let's talk about the final section, or I guess it's the penultimate one, DFD space capabilities. So this is the DFD rocket design. Credit goes to Out of This World Design. They're a real company, actually, OOTWD. And they made this design for us, and we thank them for that. So a few quotes to kind of get us started here. Although, let's see. Here, and then before I go into that. How long would burn times range, and at what range of G levels? Okay, yeah, so burn times, I guess you're saying in terms of the energy confinement time, because technically the burn times would be, I guess, throughout the mission, it would be a continuous thrust. But if you mean energy confinement time, that would be, I think, on the order of seconds or longer. And basically, it's not that everything gets lost in seconds. It's basically just saying that if you turned everything off, things would get lost in seconds. So you keep refilling it, and it keeps producing energy that you can use to keep refilling it, basically. And then what G? So yeah, it's not anywhere close to 1 G, because that's really high. Off the top of my head, I don't have the equivalent, but basically what you would get from 5 to 10 newtons of thrust. So that's and then it depends on the mass as well and things. So yeah, I would say that maybe it's like 100th of a G or something, but I would have to calculate that. So and Tim, I answered the other question too, I think. So yeah, going back to the tri-agency workshop on compact fusion. Yes, there are workshops that happen on compact fusion. It is from April 2021. We have a few big speakers mentioning some pretty important things about how fusion can be super useful for space. So we have NASA's Ron Mitchell, for example, says that compact fusion stands as a well-deserving candidate for an aggressive whole-of-government R&D initiative. Great. DARPA, right, which is the Defense Advanced Research Projects Agency, says compact fusion represents an emerging strategic technology with future potential DoD applications, Department of Defense, that is. And then ARPA-E, which is the energy version of DARPA, ARPA-E's Scott Chu, who's high up in ARPA-E and actually has gotten promoted in ARPA-E. He says that there's already a very broad stakeholder interest in compact fusion and its space and defense applications. Fusion space propulsion is possibly the lowest hanging fruit in terms of a first application for compact fusion. So it doesn't mean that developing compact fusion is easy, but it does mean that fusion space propulsion is a very clear application of it. So some space applications for DFD include spacecraft propulsion, right? So we can do large velocity changes. Here are some examples of maneuvers with high delta Vs. And yeah, maybe we can even add a LEO to L5 in order to include the L5, for HAL 5. But anyway, yeah, so we have large inclination changes, orbit transfer from low Earth orbit to geosynchronous orbit to cislunar, and also orbit transfers to L1 and L2 is what we're considering right here. Spacecraft power, so we can have high power communications, radar, space lasers, human bases, and low altitude satellites. So that's having continuous thrust, which allows orbits of 90 to 100 kilometers. And yeah, this is a figure that's from the extreme altitude fusion powered ramjet. Credit goes to Ryan Weed. So DFD enables high delta V missions without requiring a separate power source or provides lightweight portable power. So faster trips benefit from fusion propulsion. What can you do with a 1 to 2 megawatt fusion engine and a mission with a mass of 10,000 kilograms? So that's a bunch mass. So here are some examples that we have for the outer planets. Looking at Earth as from 1 AU as a baseline from the sun, we see that it would take about 1 year to get to Jupiter, which is pretty great compared to the 5-year types of missions. And that would be using 2 megawatts. It would, we can keep going, and it would take maybe around 5 years or even 4 years, depending, to get to Pluto. And as I mentioned in the earlier slides, Pluto took at least 10 years to get to. And that's just using a 0.6 megawatt. This is with the constraints of the 10,000 kilograms, right? So it costs between $10 million and $50 million to operate a spacecraft for 1 year in deep space. So long trip times delay the science return, right? And they cost a lot. So any year you can trim off is really great. And just to go into a little more detail in the NIAC mission. So this was, NIAC is the NASA Innovative Advanced Concepts. So it's a NASA funded grant that we think we got 2 of, and that was a few years ago that we did some NIAC work for a fusion reactor for space, basically looking at designs and doing some modeling. So yeah, to put a spacecraft in orbit around Pluto, you can power a lander using a laser, and then you can also return high definition video and get there in only 5 years using 0.6 megawatts of fusion energy, or a fusion engine. Sorry, yeah. So it's a pretty neat mission and shows that we can do some pretty, we have some pretty great capabilities with the DFD. And then not to go into too much detail here, but just to say that we had a vehicle design for the Pluto Explorer, and that the launch mass adds up to 10,000 kilograms, right? With all these things that are added on. All right, let's see. I guess before I answer questions, let me just finish up the Pluto part, I think. So if we compare, let's say, the New Horizons mission, which I brought up in the beginning of this talk, you know, it takes around 9.5 years to get to Pluto. It's like a 290 meter per second delta V. It was a flyby. There was no lander involved. The power at Pluto would be 200 watts, you know, 1 kilobit per second of data rate, use plutonium. You know, if we had a DFD mission, we would be able to do 4 to 5 years to Pluto, 70,000 meters per second delta V. The trajectory would be direct instead of having to do a complex swing by Jupiter. We can just kind of directly thrust, which is great. We can actually orbit the mission as a mission. We would have a lander. We would have 500,000 watts to power at Pluto, and like more than 1 million or more kilobits per second. And of course, we're using the deuterium helium-3. And we can see that we're working with higher payloads too. Like this is the payload that they had and that they could deal with. And we're talking about having a nice 1,000 kilograms of payload mass. So a lot of things that basically the bottom line that you can't do the proposed mission of DFD mission to Pluto with any other technology. So that's a really great thing. So I think to finish up this space application section, yeah, fusion transforms mission performance for space. So if we want to do cislunar transit or protect space access, do planetary defense, which I mentioned before about asteroids and comets, colonize Mars, you know, we can reduce the travel time to 3 months instead of 9 months, and can sustain a colony level payload, right, in the rocket. We can mine the asteroid belt. We can explore the solar system and beyond, right? So those are some really neat things that are enabled by the DFD. So let's take a few more questions. What transit times would you expect for a Mars mission? Oh, okay, I guess I just answered that here. So yeah, so it'd basically be around 3 months instead of 9 months. So shortens the trip and makes it more accessible for humans. Would linking the compact fusion propulsion with another propulsion system produce a more long-term space travel? So I have to think about the type of propulsion system, but I mean, in principle, yes, if you want to at least like, but I don't see that being too different from stacking with more compact fusion propulsion systems. So I would say tentatively no, but maybe yes. Sorry if that's a little bit unclear. But although feel free to figure out, follow up if you have more questions on that. For the Pluto mission, what mass of helium-3 would be required and where would it come from? Let's see if I think I had that, but I did not. Yeah, so it'd be 0.5 kilograms. So pretty small in some sense. That would be a mix of, you know, utilizing some helium-3 reserves for a startup, because, you know, it is not too much, but it would cost a pretty penny because helium-3 is a bit scarce as well. But basically that once you are abroad and, you know, you can mobilize for helium-3 mining and adding up for other helium-3 sources. There's also just the aspect that if these reactors become reach net energy, then you can also do the DD breeding, deuterium breeding, and etc. So there's some more work and talks about helium-3 acquisition, but that's the basic idea. Could a sample return mission to Pluto be accommodated? So yes, I believe that with at least with the 5-year timeline, you can, depending on the size of your spacecraft, you can do a return. But yeah, Stephanie did the original work on that mission, so we can I can get back to you on that if you have more questions on it.
I'd like to bring something up.
Yes.
Yeah, this is about the question about combining your propulsion system with others. Last month, we had Jeff Grayson, who is working on a sort of a magnetic sail that would interact with the sun's with the solar wind, the charged particles being emitted from the sun. And one of the issues they were trying to solve, and they came up with some solutions, but the issue was it's really good for accelerating going outward, right? But slowing down was a different matter. So some of the ideas I had was to interact with the magnetic field of one of the big gas giants, or the other one would be maybe using your propulsion system.
Yeah, that's a very good point.
Yeah, to get up to speed using this sun's magnetic field, use the charged particles from the sun and then slow it down with a rocket.
Yeah, no, I would agree with that. I realized that if the question was kind of more geared toward just thinking about how there could be optimal solutions of multiple rocket solutions, yes, there are a myriad of ways that we can combine DFD with other types of rockets or other types of propulsion systems. So as you give as an example there, DFD could help some systems with being able to have steady propulsion in environments where that system can't, right? So that's kind of what you were mentioning. On the other hand, sometimes DFD could actually be helped by having, in the first place, anything to get into space, we need a chemical rocket to, get it into, let's say, a low Earth orbit or something. So that's one. But two, you might want to, basically, you might want to have like a even higher thrust system to get you through certain parts of a trajectory, and then use DFD for the rest of it for like kind of the long haul. So there are different, I guess you could say, combinations you can do with different reactors, different propulsion mechanisms. That's right. So yeah, thanks for the point, Tim. That's a good point. All right, so to finish up this talk, I'll just go over current progress and kind of the path forward from here. I won't dwell too long on this since I really should be ending very soon. So yeah, we've had a lot of contractual support and have worked with the Princeton Plasma Physics Lab over the last, basically, I guess 2 decades or more, starting with the magnetic nozzle experiment and doing PFRC-1. This was the initial PFRC-2 funding from 2010 to 2016. The NASA NIAC that I mentioned, a NASA technology transfer, STTR, ARPA-E Open, and then some other ARPA-E funded grants. We also just got a Infuse grant, which is another type of grant. And so we have 3 of those for different technological developments of our antennas and other things right now. So anyway, we've had a good amount of contractual support over the years, but also, when we talk about like the PFRC-2, if we see DOE, the fusion energy sciences spending that was from 2010 to 2016, the PFRC-2 has been operating ever since, but it hasn't been supported directly, at least by like DOE since 2016. So basically, NASA funding in like this time period from like 2016 to 2019 was basically just keeping the lights on, right? It was like doing very incremental progress. So these are important things to point out in terms of like why progress can take longer or go faster is the amount of funding you put into it. So interesting point, that's all. And then the current status, this is the PFRC-2 experiment. As I showed in an early slide, it's this nice, beautiful glow and has a lot of wires and magnets and everything all around it. I was there just this past Tuesday doing some work. I was analyzing X-rays for energy and and temperature measurements. So that's there, and this is like the one of the reactor designs. So we've confirmed field reversal. We have good pulse stability that's pretty high compared to a lot of plasma timescales. And we have some decent electron heating, which is, this is kind of like hundreds of thousands of Kelvin. We're in progress right now to actually lower the frequency, to raise the power in the magnetic field, and basically get some good ion heating. That's really our next milestone in this process, to show that we can get the ions at an even hotter stage, and that our it's a good like next level proof of concept of some things that we've shown. We're kind of showing the next level of the RMF and how it works. And that's the antennas, the rotating magnetic field concept. And then the next steps forward are to achieve high field operation, to work with particle exhaust and observe that, demonstrate fusion, of course, and demonstrate thrust. So that's kind of the general path. Here's like a nice little slide of just like nice 4 pictures showing that kind of pathway that, you know, we've completed heating electrons using this RMF technique in the PFRC 1. And then in progress for late 2022, we're heating ions in the PFRC 2. So this is like the big proof of concept stuff that merits private investment. Now, then we're also doing design underway for PFRC 3 in 2023. This would be fully superconducting and would get up to fusion relevant temperatures. And this is where the value inflection happens from a proof of concept or like a proof of principle to beyond. And then for, let's say, around 2030 timeframe, we're looking to try to achieve deuterium helium-3 fusion in the PFRC 4 and achieve net electric power. And so this would be a low cost, low radioactivity fusion reactor. There's a little notional roadmap to flight going from a projected timescale of 2023 to 2033. And kind of in once again answering that question from before about would a flight take longer? Yeah, it would normally take longer, right? Because it's PFRC 3 conversion testbed, then you achieve fusion. PFRC 4, you do a flight prototype, and then you finally do your flight. So it takes some time, but we are still talking like, you know, 10 to 15 years timelines, right? So that's really significant in the fusion timescales. So I would like to end this talk by showing our vision of the future of space travel with this beautiful design made by Out of This World Design for us. And this is one of the cases where we can stack DFD rockets, 4 of them to power this spacecraft. So thank you so much for letting me talk your ear off for an hour and a half. My name is Christopher Galea. You can contact me at cgalea@psatellite.com. Or you can go to the Princeton Satellite Systems website, psatellite.com, or we're also known as Princeton Fusion Systems, the Princeton Fusion Systems website, princetonfusionsystems.com. So thank you so much for your time. I'm open to any last questions, and hope you enjoyed this talk. And also here are some references too, if you want to see any of those. But here, I'll leave this in case people want to contact.
Now, if anyone wants to raise their hand and just ask a question verbally, go ahead. Okay, we're still getting some written questions for Q&A.
So, oh, okay, yeah, I will check that. Also, am I still showing my screen?
You still are, yes.
It has the slides up right now.
Mm-hmm.
Okay, cool. So where's, oh, there we go. Right. Okay, yeah. So you're welcome, Tom. Thank you. And so for Mike, are you going to come back in 2052 to try to explain why it will take just 30 years more? That's a good question, Mike. So hopefully not. In terms of the actual development timescale, things shouldn't take that long. But yeah, it is always a question of like, you know, if funding doesn't come in, then you can't work on things, right? Like technically we have some independent product streams and revenue streams, but it's difficult, like having like enough scientific, you know, power or like people to really work on the science all together, right? Like I'm doing that myself, and then I also do other types of engineering work and everything as well. And so, and like I write proposals too to keep the lights on a bit too, as you know, my boss does and others do. So yeah, it's really a big thing about having the resources and stuff, I think. So is the magnetic field reversal temporal or longitudinal? Yeah, so it is longitudinal. And I can show that in this, maybe this figure is a nice one. So if you zoom in, you see that the background magnetic field is all going to the right. And then if you look at the center of this plasma, the magnetic field is going to the left. So it makes a nice closed loop system, basically. So yeah, hope that answers your question, Greg. And thank you so much, Marty. And thank you so much, Gregory, as well. Appreciate it. Yep, no problem.
One more thing. I noticed that with the Pluto mission,
Mhm.
you had let's see, 6,000 kilograms of deuterium, but only half a kilogram of helium-3. I take it that most of that deuterium is reaction mass. My question is, why deuterium and not hydrogen as a reaction mass or some other working fluid?
So like why instead of using deuterium for the fusion reactions?
No. I'm talking about yeah. But thing is, though, you only have a half a kilo of helium-3,
Oh,
and
yeah.
it's
Right.
roughly a 1-to-1 ratio
That's
between,
right.
or at least for atomic, at least for a total number of atoms for a deuterium helium-3 reaction. So, what's the rest of the? I'm assuming that the rest of the deuterium is reaction mass, and I was wondering why deuterium and not something else.
Yeah, so basically, one, the deuterium doesn't cost too much more because deuterium is very abundant. So compared to hydrogen, you don't have to worry too much about like the difference of that. And I think it's really just the feasibility, or how can I say, the simplicity of just having two systems or two tanks, right? Like you just have your deuterium and you just have your helium-3. So it ends up just simplifying the system. Don't have to worry about another tank of another thing and adding that as well. Yeah. Does that answer your question?
Yes.
Yeah.
Also, we have a hand raised.
Oh, do we? Also, is it Mike or is it someone else?
It's Carl.
Okay, I'll respond to Mike very quickly and then I'll respond to Carl. Yeah, so Mike just mentioned that he was half kidding on my 30-year question, but I asked a nuclear scientist back in 1966 when fusion would be available, and he said for sure by the year 2000. Yeah, no, I'm not too surprised. Sorry, Mike. That yeah, I think sometimes fusion scientists have gotten a little bit ahead of themselves, but I do think we have generally learned the lesson. Although you do have to be a little careful with kind of a lot of companies saying that we'll have something by 2025 or 2030 and stuff. So, you know, do your due diligence with any of us, right? I mean, that's us included. It's important to ask us about all of the concerns, the risks, and everything. So that's important. Anyway, yeah, thanks for attending. So yes, Carl.
Do you have any recommendations as to what educational pathway might be followed by a student interested in pursuing this area?
Oh, if you don't mind me asking, is the student like in college, or are they like maybe a student, like a aspiring student that someone in the later life that wants to like learn on the side kind of thing?
Starting out with high school, for example, and moving into college and so on.
Cool. Yeah. So the basic ideas, I mean, high school, you want to learn really well your math, your physics, your chemistry, like any science, basically. And science and math is like super important. There are obviously like, there are many ways, and there are a growing number of ways of how people can contribute to the field of fusion, right? It was different in the 1960s, where all of it was primarily just like theoretical plasma physics and a little bit of like experiment. Like nowadays, we have to think about controls. We have to think about like thermal systems. We have to think about propulsion, right? Like all these things require engineers and scientists from all walks, you could say. So I think with that said, like, you know, and have them keep tabs on things like this. You know, if there's any kind of educational areas or like universities that they can like maybe talk to like a professor or a scientist, that's really great. But yeah, I would say really have a good foundation in math and physics will like super benefit you. In terms of how you do that, you know, you can maybe join an Olympiad or something too, but it's really that passion for really learning and wanting to make good changes, right? And so that kind of brings you into physicist to engineer spectrum, wherever you land in that.
Okay, thank you. And thank you for your presentation. It was informative and interesting.
Yeah, I'm so glad. And thanks for your questions, Carl. Yeah, I hope I answered all of them sufficiently.
Thank you.
Yeah.
Any other questions?
Also, it looks like, what is it? I think someone mentioned about getting a head count. Did you do that, Tim?
Oh yeah, I have already got that head count. I got it wrote down. It's about 64 total. That would be you, me, Fred, and 61 people attending.
Cool. Nice. Great.
Yeah. Also to Carl, I tried to get in touch with you on earlier through email. I don't know if you ever got my email or not.
Oh, am I still on?
Yeah, you're still on.
Oh, okay. I just opened the email a few days ago. Been pretty busy. Had some relatives come over from California, my grandchildren, and been pretty busy with them for a while. So, yes, I'm getting to it.
All right. That's good. Any other questions? I believe that's it.
Great. Well, thank you so much. It was nice meeting you all.
Thank you. Nice meeting you.
Oh, so yeah, I guess I'll sign off now then.
All right.